Okay. Okay. Is it okay? Yes. So my talk will be more on mathematical aspects of cryptography, how mathematics plays a role in cryptography, classical cryptography, as well as public key cryptography. And in the end, we will discuss about the fate of the public key cryptography in the quantum world. So what will happen to the quantum algorithms? So what the quantum algorithms for classical problems behind cryptography. So we will start with very basic notions, and I'm sorry for the experts here if you know it already. So especially for the faculties here. So what is cryptography? And cryptography is sure. Okay. Yes. Cryptography is a study or methods to send messages, to receive, to interchange messages in a disused form. So that if, for example, if these two people, Bob and Andy and Sam, if they want to communicate messages, we always have a third person who interprets their messages. But we don't want the third person to know what they are communicating. For example, if we have OTP, the communication is always between ourselves and the bank. We can think of Andy is ourselves and Sam is a bank, and we always communicate OTP between us. But there is always a third person who wants to interrupt the OTP, but we don't want the third person to know what is the OTP we are communicating to each other. So we want to communicate, but in a disused form. So how do we do that? So before going to that, we will see some terminology. So the plain text. When we say plain text, we always mean the message, the sender, the message we want to send. What we want to send, we call it as a plain text. And ciphertext, we mean the plain text in a disused form, in a changed form. So a disused message is called the ciphertext. And the process which changes the plain text into a ciphertext, we call it as encryption. And the process which changes again to a ciphertext into a plain text, we call it as a decryption. So these are basic notions we want to know when we understand this cryptography. Okay, let's start with the cryptography, which at least 2000 years old. It's a cipher, shift cipher. It's a very elementary cipher. It's easy to understand. Suppose we want to send the message, and so before starting this, the references for my lectures are two things: mathematical cryptography by Silverman and mathematics number theory and cryptography by Neil Kopitz. So these two are the references for my talk. Okay. Suppose if we want to send a message, enemy falling back. So, but how do we send that? The Caesar cipher says that one way is that you arrange the letters in the syntax in a single form, in a single context form, EN, EMY, FA, LLI, and so on. And then I say that replace E by J, N by S, E by J, M by R, Y by D, and so on. So here I'm replacing each letter, each English alphabet letter by some other letter. But I don't have any pattern in that. I just simply say I change the letters, plain text letters into a ciphertext letter, and then I send this message, this sentence. So the sentence below. So it's very clear that one cannot read what is the sentence here, because it is words without any meaning. And once somebody receives, a receiver receives this message, and he or she needs to know how do we replace J, S, J, R, D, K, and so on. So if they know that, how do we replace these letters? And suppose if they know that I replaced E by J, they have to replace J by E. And N by, if they know that I replace N by S, I replace S by N, and so on. If we do that, if we make it a replacement in every ciphertext, remember it is a ciphertext and it is a plain text. So if you know the process, if they know the process how the plain text changes into a ciphertext, they can easily change the ciphertext into a plain text, and they can read it as enemy falling back. And at first moment, it looks fine, right? It looks very good because nobody can read JL, JRB, they can read what is there in the ciphertext, and it looks very good. But the problem is there is a pattern. We have a pattern in here. We have a pattern. If we understand the pattern, it is easy to decode. It is easy to change the ciphertext into a plain text. So how do we do that? So before going to that, we just quickly recall the mathematical background, what we need to know for understand these cryptography protocols. So okay, let's have an integer m. So m is always an integer m, a positive integer m, together are equal to 1. And if we say that a congruent to b modulo m, we mean that m divides a minus b. So modulo m, so that we might have studied in high school. So when we say that a congruent to b modulo m, we mean that a and b, a minus b divided by m. Or for example, here let's take m equal to 12. Suppose if our m is 12 and if our a is 6, then I can say that 6 is congruent to 18 modulo 12, because 6 minus 18 is 12, minus 12, and minus 12 is divided by 12. So 6 is congruent to 18 modulo 12. And if we take 9, I can say that 9 is congruent to 45 modulo 12, because 9 minus 45 is 36, and which is divisible by 12, and so on. Okay. So here we want to understand this notion. A is congruent to b modulo m, and then we can say that once we fix an integer m, then I consider this set. What is this set? This set is all integers starting from 0 up to m minus 1. Up to m minus 1. So if by m is 12, then this set z by m is z by m is a set 0, 1, 2, 3 up to 11. So what is special about this set? What is special about this set? If you take any integer, that should be congruent to at least exactly one of these integers in the set. Can I write it? So if we take this m is 5, if I take m equal to 5, the set I am interested in z by 5 is that. So we have a mathematical meaning for it, but we don't need to worry about that. So then this set is 0, 1, 2, 3, 4, 5. So z by 5 is I made a mistake. So it is not 5. Correct. You are absolutely right. I'm wrong. So this is the set starting from 0, 1, 2, 3, 4. So what is special about that? If you take any integer, that should be congruent to exactly one number here. For example, if we take the number a is 101, so 101 is congruent to what number here? So I can say that 101 is congruent to 1 modulo 5. 1 modulo 5. 1 modulo 5. So if we take another number, let's say 153. So 153 is congruent to 3 modulo 5 here. So if I take the number minus 54, and I can say that minus 54 is congruent to 4. What? Minus 54 is congruent to, it is here. So minus 54 is congruent to 1 modulo 4. 1 modulo 4. So if I take the number minus 55, I can say that minus 55 is congruent to 4. 4 modulo 4. 4 modulo 4. So minus 54 is congruent to 1 modulo 4. 4 modulo 4. So minus 54 is congruent to 1 modulo 4. 4 modulo 4. So minus 54 is congruent to 1 modulo 4. 4 modulo 4. So minus 54 is congruent to 1 modulo 4. 4 modulo 4. So minus 54 is congruent to 1 modulo 4. 4 modulo 4. So minus 54 is congruent to 1 modulo 4. 4 modulo 4. So minus 54 is congruent to 1 modulo 4. 4 modulo 4. So minus 54 is congruent to 1 modulo 4. 4 modulo 4. So minus 54 is congruent to 1 modulo 4. 4 modulo 4. So minus 54 is congruent to 1 modulo 4. 4 modulo 4. So min 1 modulo 4. So because minus 54 minus 1 is minus 55, which is leaves 55. So we can say that if I take any number, which should be congruent to exactly one of these numbers. Okay. So yes. So we want to know at least two properties about this set. Two properties about this set, and we will not prove those properties. We just state it. So what? Any question? Yeah. So if we take this set has an addition. This set has an addition. We can define addition and multiplication for this set itself. So we know addition and multiplication for real numbers, but here we can add two numbers here and we can multiply two numbers here, but not the usual way. Suppose if I take a number here and if I take another number here, I want to add these two numbers. And how do I add that? So I add a plus b. By definition, a plus b, I say that which is congruent to which is so if I take a number a here and b here, I can add a plus b modulo. That means that I divide m by a plus b and take the remainder, and that is the addition of a plus b. And for example, if my m is 5 and our a is 1 and b is 4, what is a plus b? Or a plus b here in this word is that a plus b is 5. When I divide 5 by 5, I get the remainder 0. So here a plus b is 0. So when we take, if my a is 3 and our b is 4, our a plus b is 3 plus 4, which is 7, which is 2 modulo. So a plus b is 2. So the thing is that if I take this set, I can add two numbers in this set. I can multiply two numbers in the set. I can add two numbers, and I have the addition also a number in the set. And I can find the inverse of every element in the set. For inverse in the sense the negative of a number. For example, if integers, the negative of 2 is minus 2. Right? Why is minus 2? Because when I add 2 with minus 2, I get 0. But here, when I have this set, for example, modulo 5, when I go for a is 3, what is minus a? Here minus a is, I should find a number in the set so that if I add with that, I should get a 0. So what number should I take here? 2. So minus a is 2. So it is not minus 3, it is 2 here. So if a is 4 and our minus a is 1. Correct, you are right. If our a is 3, our minus a is, I write it. If my a is 4, minus a is 1 and so on. So we need to find, so what we want to say is that for this set I can define addition. So for that addition, I have the addition also an element in the set. I can find the inverse of an element, and also I can say that if I add 1 and 2 and 2 and 1 they are the same. So these properties it has. But when we go for the multiplication, so how do we define multiplication here? So there we have a problem. So if I have this set, let's have z by 6z. Let's take this, which is 0, 1. How do I get it? So how do I add? So like this, so addition, as I said earlier, if my A is 2 and B is 5, our A plus B is 2 plus 5, but we are working in the world of modulo 6, so which is 2 plus 5 is 7, which is 1 modulo 6. 1 modulo 6, that's done. So when we go for the multiplication, here, I denote the multiplication by dot. So here A dot B is 2 into 5. So any guess how do we define the multiplication? We do the usual multiplication and go modulo 6. So it is 2 into 5 is 10. So what do we modulo 6 we go for 4. So A into B, in this case A into B is 4. But here we have a problem. The problem is that if I have an element A is 2, if my A is 4, can I find the inverse of A? Inverse with respect to multiplication. That means 1 over A. In general, real number system, I have 1 over A is the inverse of 4. So 1 over 4 is the inverse of 4. But here, what is the inverse of 4? Inverse of 4 should be an element here. When I multiply with that element, I should get a 1, right? So I cannot, so let me check whether any number here I can multiply with 4, I can get a 4 here. I can multiply 1 with 4, I get 4, that's the element. 2 into 4 is 8, which is 2, so that's 2. 3 into 4 is 12, which is 0, I get 0. 4 into 4 is 16, which is 2, so I get element 2. 5 into 4 is 20, which is I get 2. So what we observe is that I don't have an inverse for 4 here. I don't have an inverse for 4. That means that I cannot find an element here. So that if I multiply with that element, I will get a 1. So that plays a crucial role in cryptography. Finding a multiplicative inverse of an element plays a crucial role. But here, so we are unlucky here, but in a special case, so I am not going to prove that if our m is a prime number. So if m is a prime number, then if we consider the set z by pz, which is all numbers from 0, 1, 2, 3 up to p minus 1, this set behaves like a real number system. That means I can multiply two numbers and I can find an inverse for any numbers. For example, I will prove that because that's very interesting to know that if my p is 5 and if I take the number, then my set is z by 5 z is 0, 1, 2, 3. I have a table. Yes, I have a table. Yes. So if I take the 5, so let's have modulo 5. So I have the set is 0, 1, 2, 3, 4. Therefore, if I add, so that this represents the addition table. So I can see that 0 plus 0 is 0, 1 plus 0 is 1, and so on. So for addition, there is no problem. It has everything. But when we go for the multiplication, we just noticed that we don't have an inverse for in z by 6 is there. But here, let's see that. So I have a 1. So I need to find an element in the set. When I multiply that, I should get a 1. So clearly, I multiply with 1 itself so that I get a 1. For 2, I multiply with 6. So 2 into 3 is 6. So modulo 5 is 1. So I get a 1. And then for 3, the inverse is 2. So 3 into 2 is 6. So by modulo 5, I get 1. So for 4, so 4 inverse of 4 is 4 itself. 4 into 4 is 16. Modulo 5, I get a 1. So here, in this example, we see that when we go for modulo 5, every except 0, for 0 there is no inverse. In any world there is no inverse for 0, not only in the real world. In any abstract world, any mathematical structure, 0 will not have an inverse, unless otherwise we define it on ourselves. But it is not natural, even if we define it. So 0 will not have an inverse, except 0, if we take any non-zero numbers, we have an inverse. Here we have an inverse. So the same thing works in any general prime number p. So how do we find that? So to find an inverse so not only that, and in this example, inverse of every non-zero element exists. If we take any prime number except 0, we have an inverse. So how do we prove that? And we use Euclidean algorithm. Euclidean algorithm is nothing but the division algorithm. what we use in our elementary school. Division algorithm. You divide a number by a non-zero number. So how do we do that? Suppose I have two numbers. Let's try to understand extended division algorithm. So which helps us to find. So remember, I have an A here. So I'm considering Z by PZ. And then in this set, I consider an element in this set which is non-zero. So I want to find an inverse, multiplicative inverse of A. So to do that, let's try to understand extended division algorithm. So what is the extended division algorithm? Suppose if I have two integers, A and B, and I assume that A is bigger than B, bigger than or equal to B, then what do? I first divide B by A by B, sorry. I divide A by B. So divide A by B, I get the quotient and the remainder. The only thing is the remainder is less than the divider. That's the only thing. So if the divider, suppose if the divider R2 is bigger than 0 and less than B. So if that is the case, so if R2 is 0, then I stop here. In that, if R2 is not 0, then I go to the next step. What do? I divide B by R2. I divide B by R2, I take the quotient and the remainder, and then I see the remainder, I see the remainder. If the remainder is 0, then I stop at the second stage. Otherwise, I go to the third stage. What is the third stage? I divide R3 by Q2. I divide R2 by R2. I divide divider by the remainder. I divide the divider by the remainder. R2 by R3, I get the quotient and the remainder. So if R4 is 0 here, then I stop at the third stage. Otherwise, I continue that. So how long this process will go? So we need to see that, right? This algorithm stops somewhere. So my claim is that this algorithm should stop somewhere. So why it should stop? Because look at the table below. I have a B, and then I have B is bigger than R2, and then R2 is bigger than R3, and then R3 is bigger than R4, and so on, and so on. So because remember, I go for RT. No, it's my notation. I use it for we can call it as R1 and R2. So it's my notation. So RT and so on. So we have this one. So in each step I have RT, right? It should stop somewhere. Why it should stop? Because each Ri's are non-negative numbers and they are strictly decreasing sequence. It should go to 0 somewhere, right? So there is a saying in Tamil, I don't know that my professor RSM said that, I hope if non-Tamilians should apologize to me. So Kundri Thinnal, what is the pardon me? Kundi Thinnal Kundrum Karai. That's an example when he said, because he taught me good algorithm. So when I started understanding this extended algorithm, he said, look at the sequence and say what do you remember. He's a very old person. He said that see, you have a sequence, decreasing sequence, it should stop somewhere. It should go to 0 somewhere. So I assume that at RT plus 1 it should go to 0. That's it. So once it goes, that means that we have an algorithm, and we have an algorithm. So we have an algorithm which should stop somewhere. Once it stops, take the last non-zero remainder, RT. So that is the GCD. So this algorithm helps us to find the greatest common divisor of A and P. And the complexity of this algorithm, I'm not going to discuss the complexity, and you can see that you can find it in the book Number Theory and Cryptography by Neil. So the complexity of this algorithm is vaguely, by looking at log QE, big O of log QE. It's not so that means that algorithm is a very easier one. It's a logarithmic complexity. So it's a polynomial algorithm. So finding a GCD of A and B is not a big deal. So you can easily find that. So you can see that even if my A is 10 to the power 100, 10 to the power 100 is a very big number. 10 to the power 100 is a very big number. What is 10 to the power 100? It's a Google number, right? It's a very, very big number. You cannot even imagine that number, 10 to the power 100. Even if that number, if we take for A, So that will take log cube of A is only takes 100, only takes 1 lakh steps. So 100 cube, yeah. No. Yeah, so we have 100 cube steps. That's not a big deal, even for that one. So, okay. So let's have an example. So we always have an example to understand our theory. Let's say A is 2024, it should be 2025. Because I made this guy slide last year. That's why I'm doing 2024 and A B is 748. So to make this, so I want to find the GCD of A and B. So by external algorithm, we use the external algorithm to find the GCD. So I divide 24 by 748. So the quotient is 2, the remainder is 528. So the remainder is not 0. So therefore next step I divide 748 by 528. So I get the quotient is 1 and remainder is 220. And then see that 220 is not 0. So then I divide 528 by 220. I get quotient is 2, remainder is 88. Again remainder is not 0. Then I divide 220 by 88. I get the quotient 2, remainder 48, 44. Again it is not 0. Therefore then divide 88 by 44. The remainder is quotient is 2, remainder is 0. So inclusion algorithm says that you stop at the stage where you get the 0 remainder. Then you look at the last non-zero remainder, 44. So that 44 is the GCD between 2024 and 748. So that's it. So that's one way. So that is one way to understand that. So there is one more application for the external inclusion algorithm. So what is an application? So the application is the following. So for the first application is, so this repeatedly doing the division algorithm for 2 integers, eventually we will find the remainder, we will find the GCD of A and B, 2024 and 748. And the one more thing is that, so look at the last, look at the first number, look at the first equation. So first equation, which is, this one is A. So this one is A and this one is B. If we replace, if we rewrite this by A and B, we have 528 is equals to A minus 2 times B, right? The first equation is simply that 528 equal to A minus 2B, and then yes. So look at the second equation. The second equation becomes, so if you replace first equation, the second equation, instead of 528, I replace A minus 2B here. If replace A minus 2B here, I will get 220 equal to minus A plus 3B. So we can easily check that. I just replace 528 by this first equation. So I get 220 equal to this. And then I go to the third equation. What is the third equation? So third equation is nothing but 528 equal to 220 times 2 plus 88. So here I replace 528 by this equation and 220 by this equation. If I do that, I will get 88. So what I do? So I replace, I do it ahead. So I have, so third equation is 528 equal to 220 into 2 plus 88. So here, instead of 528, I put the A minus 2B. Instead of 220, I put minus A plus 3B. If I do that, I get 88 equal to 3A minus AB. So once we do that, I look at the last equation. The last equation is 220 equal to 88 into 2 plus 44. I replace 88 by this equation. And then 220 by this equation. If we do that, we get 44 equal to minus 7A plus 90B. So here, remember our A is yes. Our A is 2024 and our B is 748. Right. So here the important of this equation is that I represented the GCD. Remember 44 the GCD. I replace the GCD of A and B. A and B is minus 7 times A plus 19 times B. So I can express the GCD as a linear equation of A and B. So that's the advantage for this equivalent algorithm. So now let's come to the point. I just said if I take a prime number, every non-zero element should have an inverse. Let's take P is a prime number, then in that case, if I have a number in between 1 and P minus 1, and then I take the GCD of A and P. If P is a prime number, what is the GCD between A and P? What is the GCD? 1, right? The GCD is 1 because P is a prime number. So what is the property of prime number? P is a number which is divisible by 1 and P. So no other number which is less than P which may divide P. So because I have a which is less than P minus 1, less than or equal to P minus 1, so definitely A will not divide P. Sorry, any number which is bigger than 1 will not divide P and A both. Therefore, there should be only one which can divide both A and P. So 1 is a GCD. We just observed that our A1 can be expressed as A linear combination of A and P. That means there is integers Ax and y, so that 1 is equal to Ax plus Py. So now I consider this equation modulo P. So for the left hand side, what is 1 modulo P? 1. What for right hand side, what is the Ax modulo P? Which is Ax, because I don't know what is A and Ax. I have Ax. But for this P into y, what is Py modulo P? 0. So I have 0. So Ax plus 0 is Ax. So I have Ax modulo P. So here x is the inverse. So here I can able to find a x so that when I multiply A and x, I get a 1. So this extended equivalent algorithm says that so the moment you go for a prime number, a prime field, the moment you go for the prime world, whenever you choose a number A bigger than 1 and less than P minus 1, you always find a x. When you multiply with A into x, you get a 1. So we don't know what is that x. But the extended equivalent algorithm says that you can find it. It gives a procedure to find a x. So that works in log 2 to log 2 complexity. So but if we have a P and A and we can find the x, what should be a x also. Okay. So I skip here. So an application is that A and B will be two positive integers. If the GCD of A and B is B, then by the external algorithm, you can always find two integers x and y, so that Ax plus By is equal to B. And using that, we will try to express GCD as a linear combination of 2024 and 748. Okay. Now, so all the hard work is done. So now we go to that's a mathematical part we know we want to understand for our cryptography. Okay, let's go to let's revisit our Caesar cipher. I said, so initially we said that it is difficult to understand because I replaced E by some other alphabet, N by some other alphabet, E by some other alphabet, and so on. But it is not an arbitrary alphabet. It is not it is not like a permutation of 25 letters alphabet. But here there is a pattern. So how do we understand that pattern? The pattern is the following. So to understand the pattern, let's write the English alphabets A, B, C, D, E, F, G, H, I, J, K, L, M, N, and so on. So, but I named the first alphabet by 0, A by 0, B by 1, C by 2, E, D by 3, and so on, and last letter alphabet Z by 25. So first I changed the English alphabet into a mathematical object. See, so you want to understand mathematicians. So there are many physical problems, but if you say it in the same way to the mathematician, they don't understand that. So you have to give it to them in their language. So first you go to the mathematical world, you should convert them, you should say, no, this is the thing. So you will not understand what is that. When you say, no, 0, 1, 2, 3, it's around that. So we understand these numbers, in some extent. So I get 0, 1, 2, 3 up to 25. So once I do that, I have the message, enemy falling back. So that statement also I change it into a string of numbers. So I know that what is E? My E is 4. And then I know my N. My N is, I know, is 13. My E is again 4. M is 12. Y is 24 and so on. And my K is, my last one K is 10. So this is our plain text. This is our plain text. So don't think that even this letter there is no meaning. Okay, this is a very, you can say that you can simply send this string of numbers and you may not be able to read that. That's a whole method. You can just simply changing an alphabet into a mathematical by numbers is a very, everybody knows. So it may not work. So we have to work harder. So 14. So now our plain text is 14, 13, 4, 12, 24, 5, 0, 11, 11, 8, 13, 6, 1, 0, 2, 10. So once we have the plain text, Caesar says that you change the plain text into a ciphertext by adding 5 modulo 25. So 5 modulo 25. So I replace 4 by, I replace every number a by a plus 5 modulo 26. Because we have 26. So I replace 4 by, so 4 plus 5 is 9. There is modulo 26 also it is 9 and so on. So 13 plus 5 is 18. 4 plus 5 is 9. 12 plus 5 is 17. 24 plus 5 is 29. But we may not write 29 here. But we should go for modulo 26. So 29 modulo 26 is 3. Yes, right. 5 modulo 5 is 10. 11, 0 modulo 5 is 0 plus 5 is 5 and so on. So I replace every plain text here into a ciphertext. So my ciphertext is modulo plus 5 modulo 26. That's it. So once I do that, so I need to send it again to the receiver. So the receiver, what I just need to do? I just need to replace each alphabet numbers here by the corresponding alphabets. So I replace 9 by 9 corresponds to what? Look at the naming. 9 corresponds to J. So 9 corresponds to J. 9 corresponds to J. 18 corresponds to S. So 18 goes to S. Correct. 18 goes to S. And 9 goes to J. 9 goes to 9 goes to J and so on. So this is our plain text. So the same plain text. So now they may send it. So now they can use this as a plain one. But the problem is that, so remember, what is the encryption? The encryption process here. The encryption process is going plus 5 modulo 26. It's a function, right? It's a function. You can think of the encryption as a function. You can think of encryption as a function from the set Z by 26Z to Z by 26Z. What is that function? The function is f of A is A plus 5 modulo 26. So so encryption is now behaves a mathematical object. So that mathematical object is a function from this domain to the domain. But once the receiver receives this message, they have to find they have to go from ciphertext to the plain text, right? So how do they do that? They have to find the inverse of this function. So what is the inverse of this function? What is the inverse of a function? The function from the domain to f is a function. What is the inverse? So inverse is a function from the codomain to the domain, so that when we go for the composition, I should have same element here. So what is the inverse? So what is the f inverse? So I should have a f inverse here. F inverse from the codomain. Here unfortunately, the codomain also the same set. Domain also the same set. For the codomain to the domain. So I need to say that I need to make sure that f composition, f inverse is the identity function. Is it so? Identity function, right? So let's see that. F of A, what is f of A? A plus 5 modulo 26. And then I need to apply f inverse. What is f inverse of that? So f inverse of that is, so I write it here, f inverse of that is A plus 5 minus 5. So A plus 5 minus 5 is A modulo 26. So I start with A and then I end up with A. So that means the function what we define is the inverse function. So I have the receiver. I just need to apply the f inverse function for this function to change the ciphertext into the plain text. So that's what exactly we are going to do for the decryption. For the decryption, so what they need to do? So they need to say that they subtract 5 from each of the ciphertext alphabets. So 9 minus 5 is 4. So 4 corresponds to J. Sorry, 4 corresponds to E. 18 minus 5 is 13. 13 corresponds to N, and so on. So if we write it, we will get it N falling back. That's right. So, but the problem is that with this procedure, with the cipher, if you use Caesar cipher, it is easy to decrypt. Anyone can decrypt that. Because so this 5, so here I mean, we converted a plain text into a cipher text by adding 5 to the plain text. So how many such numbers are possible? You cannot add 0. If you add 0, the plain text is same as the cipher text. That you cannot do. So you can add 1, you can add 2, you can add 3, you can add 4, up to 25. You can only use numbers 1 to 25. You can only use numbers 1 to 25. If our enemy knows that if you used Caesar cipher to decrypt our message, they can easily solve this problem even with computers in milliseconds. Even with hand, it's only a matter of 5 or 10 minutes. So it is not at all a secure way of sending message, but it is a very good method to start with to understand our cryptographic protocols, how it works. So the take home for this procedure is that we have the domain. We have the domain G by 26 is there. It is always our domain because we fix with the English alphabets. We can use any alphabets if you want. G by 26 is there. The idea is that you need to find a function. You need to find a function from the domain to the codomain so that the f inverse exists. We should have f inverse. So the moment you find a more complicated function from the domain to the codomain, you have a better cryptographic protocol. Okay. So let's write the Caesar cipher. So the Caesar cipher we can write it as follows. The plain text for us from now onwards, the plain text is always a number from 0 to 25, and the cipher text is also a number from 0 to 25, and we should find an encryption function. The encryption process is simply a function from P to C. So here for the Caesar cipher, we use f of p is p plus 5 modulo 26, and the decryption function is f inverse of c is c minus 5 modulo 26. So that's the thing. Okay. So we can generalize this procedure. How do we generalize that? We can replace n by any alphabet. N is because we may use any language, right? If in English we have 26. For any language we can use that. So I replace 26 by n. So then in that case our plain text would be any number from 0 to n minus 1, and ciphertext also a number from 0 to n minus 1, and I need to find a function from f from p to c. I define the function f of p is ap plus b. The only thing is my a and p are inverse to each other. So my a and b, so here I define f of p is ap plus b modulo n with the fact that GCD of a and n is 1. If we have this property, then I can define this function. Instead of simply adding, I can take ap plus b is a function from b to c. And for this function, the inverse is a inverse c plus minus a inverse b modulo n. Remember, a inverse is not the inverse what we want. It's not in the real world. It's a modulo n. The a inverse is a inverse of a modulo n. So that's why we are taking GCD of a and n equal to 1. So the moment I say that a and n are equal to 1, the GCD between a and n equal to 1, I can use extended algorithm to find the inverse of a. So otherwise, for if a and the GCD of a and n is not 1, then I cannot use this function as a encryption function from P to C because it doesn't have an inverse. We should have a function which so that it has an inverse. So if we define such a function, then we have an inverse what we define here, and we can use this as an encryption process from P to C. Okay, so that's one way to understand that. For example, let's say, for example, if my n is 26, I go back to same example. If my n is 26, I take my a and b. A is 7 and b is 3. Look at a. So we have carefully taken a equal to 7, so that a 7 and 26 are there is no common divisor between 7 and 26. So I cannot take 8 here, because the moment I take 8, the function 8x plus 3, there is no inverse. There is no inverse function for that. I cannot take that. So I take a is 7, so that carefully. So a is 7, so that a and 7 and 26, the GCD between 7 and 26 are the 1. And then I define a function f of x equal to 7x plus 3, which is a function from the domain to the codomain. You can use it as an encryption function. And what is the decryption? The decryption function is use the formula, previous formula. What is that? A inverse c plus minus a inverse b. So which we use. So I'm not going to calculate that. So you can see that f inverse of y is 15y minus something. So which is the inverse of here. So now we can easily use this as an encryption function and this as an decryption function. But the important thing to notice here is that if I know, if the receiver and suppose if the receiver and the sender, if they know F, they clearly know F inverse. They don't need to know F inverse and F simultaneously. Why is that? If somebody knows F, 7x plus 3, what they need to, simply they need to find the inverse of 7 and then multiply by the inverse of 7 and then so inverse of 7 and then they use this one, a inverse c plus minus a inverse b. So they don't need to find know of both f and f inverse. They just need to know only f. If they know, if the both receiver and sender, if they know f, they can easily use. They both know both the encryption and decryption what it works. So let's go to Wigner cipher. So because we want to make the possibility, even in this case, so it's a generalization of Caesar cipher. Even in this case, it is not secure. Why is it not secure? Because the function what we are working is that ax plus b. So a is maximum, it has 25 numbers. Maximum, so it should be less than 25. But it has maximum 25. So even if you take 25 to 25, 625, you only have 625 keys. And if somebody knows that you are using this encryption procedure to decrypt your message, they can easily check this 625 procedure and they can see what the message was. It's just a matter of seconds using a modern computer. Okay, so now we want to make, so these things are very old encryption system, but we just want to understand publicly things so that we will see what is the problem in the quantum. Even the strongest one, what we are using now, may not work in the quantum world. So we want to go step by step. So let's go to Wigner cipher. So how do we understand Wigner cipher? So Wigner says the following. He says that don't look at the, so remember Caesar cipher. In Caesar cipher, each alphabet considered as one block. Right? He replaced each number by one number. He encrypted each alphabet in plain text into another plain. So Wigner says that don't look at that. So consider as a block. So suppose, for example, he says that suppose the message we want to send is the following. But how do we mean that? This crypto system is not secure. So how do we, suppose if you want to send this message, he says that, so don't look at each alphabet as a block. Consider a certain number of alphabets as a block. So he said, for example, here we are taking 6 numbers. Consider first 6 numbers, and then next 6 numbers, next 6 numbers, and then the next 6 numbers, and then we have only 3, and then you can replace by any number, any dummy alphabets. So once we do that, so he says that replace, replace this block into your plain text, first numbers. I know that T is corresponds to 19, H corresponds to 7, I corresponds to 8, S corresponds to 18, C corresponds to 2, R corresponds to 17. So first consider the first 6 block, and then cipher text change, do the encryption for the complete block. How do you do the block? For that you choose the 6 numbers and we add these 6 vectors into this. So basically what we did here, so let's understand this first. So taking the first alphabet, this one corresponds to 19, 7, 18, 8, 18 to 17. And then replace this complete thing by adding this one with this one. Of course, model 26 again. So if you do that, 2 plus 19 is 21, so I get 21. So 7 plus 8 is 15. 15 plus 8 is 23, I have. 7 plus 18 is 25, so I have 25. 4 plus 2 is 6, I have 6. 17 plus 17 is 34, but we should work for model 26. So model 26 it is 8. 17 plus 17, 34, and model 26 is 6. So I have this one. So what we did here, instead of changing each alphabet, so there the encryption key is only one alphabet, right? Only one number. 5 is the only. I use 5 to encrypt a message, plain text into a ciphertext. Here I use a vector. Right here I use a vector. What is a vector? What is a vector? Arrangement of numbers in any order, whatever, in any order, let's say that, but into finite sequence of numbers. So here I changed the key. There it was a number. Now we have a vector. Replacing here, I replaced the plain text by, I replaced key by a vector. So here I replaced, I added this with this vector like this. So in this way, what we can do, Weakness says that you can consider the plain text as a vector and ciphertext as a vector. I started with this. I said change the plain text into a mathematical object. So initially I changed the plain text into a mathematical object which is a number, right? So now because we have multiple objects, we have many mathematical objects, vectors, matrices, groups, rings, and whatever you want. So replace it. We just need to replace the alphabet into some mathematical object. But now we know that apart from numbers, we know that vectors are the another object which is we know it already. So I replaced a plain text is a vector. A vector. So what is a vector? It's arrangement of I saw it as how many D pair of So Weakness says that with the ingenious idea is that replacing a mathematical number by a vector. So here in this case our plain text is a vector of size D. Of course each element in the vector is an element from Z by N Z. And ciphertext is also a vector of size D, and each element in the vector is an element from Z by N Z. And what should be the key? A key should take a vector here and a vector here. What that should be? That should also be a vector. So if I take any vector, K1, K2, Km4, and Km here, it should be of size N. So if I take any vector of size N, that will work as a encryption key. So I can replace any plain text into a ciphertext key. So if I take plain text is x1, x2, xm, the function, so remember what is the encryption, is a function from P to C. So if I x1, x2, xm is an element here, f of x1, x2, xm is x1 plus k1, x2 plus k2, xm plus k. But we should remember that the addition is not a usual addition, it's addition modulo m. Sorry, addition modulo n. Addition modulo n. So what is the decryption? So once I have an element in the codomain, so f inverse of y1, y2, ym is y1 minus k1, y2 minus k2, ym minus k. So I just need to subtract k1, k2, km so that I get the vector. So that's what Weakness says. Weakness says that you replace a number by a vector. So what should, okay. So that's a Weakness thing. So what should be the other one? We should go one step ahead. So I replaced a plain text into a number first, and then placed a plain text into a vector second. Then what other way we can replace a plain text into a matrices. We can replace plain text into matrices. That's what we'll see inside the matrix. See here what we do, we replace plain text into matrices. So we know matrix theory. We have been studying for a long time. So we know how to play with matrices. So that's what we exactly do here. Suppose our plain text is this one, no answer is our message. No answer is the message we want to send. So I want to change my plain text into a matrix. So one way is the following. How do you do that? I take first two pairs, NO, AN, SW, ER, and then I consider the NO. What is NO corresponds to the number N corresponds to 13, O corresponds to 14. So I replace NO by the column matrix 34. So AN corresponds to AN I replace by the column matrix 0, 30. How do I do that? I take the first number here is corresponding to the number A, which is 0. N corresponds to 30 and so on. So SW corresponds to 18, 22. AER corresponds to 14, 7. So now I say that there is a way to, now I know that there is a way to change the plain text into a